Okay. Good morning. So, a couple announcements. First, I know everybody wants their test back. The exam 1 grades. I haven't actually gotten to your section yet, so I've got 3 other sections that I'm grading. My goal is to get them in today. The drawing pad that I'm working with isn't working, so I've had to type my comments. Things are going a little slower than they normally do, but they should be in today. If not today, then tomorrow. Tomorrow at the absolute latest, but my goal is always to get them in within 1 week of the day of the test. So I will work until around 9-10 tonight. If they're not all done by then it'll have to wait till tomorrow, but should be in by the end of the day today. The other announcement is homework 6. This has been pushed to Wednesday. Your class, we did actually get to finish all of the theorems from section 7.8, but I want to get a little bit more practice with them, and I want to give you guys a little bit more time to really internalize them. So yeah, so homework 6 is not due today. It is due Wednesday. That also is a little bit more fair since it opened last week a little bit late. I'll give you guys a week to work on it. Today, we're going to discuss a little bit more the theorems from section 7.8. And then we're also going to introduce sequences, which is section 11.1. So after we finish chapter 7, and 7.8 is the last section in chapter 7 that we cover here at Santa Fe, then we jump to chapter 11, which is the next bit of the book that talks about convergence. A quick reminder, we are in this middle third of the course now, where it's all about convergence. And after today, well, today included, from today on, the issue will be more of answering the question of convergence than anything else. The calculations are important, but they're becoming much, much less important compared to the logic. So make sure that you're paying attention to the words you write. Don't skimp on writing the words in your solutions. I know that WebAssign is WebAssign. A lot of the times you just click a button that says converge or diverge. That's not sufficient when it comes to writing out your solutions. So I want you to pay careful attention to how I solve the examples and model that. By doing a good job here in these early sections where the convergence questions are not terribly hard, you will prepare yourself for the latter problems when we get into dealing with series and power series, where the questions are much more difficult and the logical flow requires a little bit more critical thinking. So getting yourself used to the sort of if-then structure of these theorems and employing the tools of first-order predicate logic, you will develop a sense of what works and what doesn't as far as the phrasing is concerned. So please pay attention to the vocabulary, write in full sentences, think about your solutions, and most importantly, share them with other people. That's really the biggest thing. So I want to ask and answer honestly. I'm not going to butt in if the answer is yes, but have you guys created a GroupMe or a Discord or anything like that for this class? Again, a yes or no is sufficient. I'm not asking for links. I'm not asking you to let me in. I just want to know, is there such a thing?
Yes.
Yes. Okay, good. Does everybody have access to it?
I'm not sure.
Okay, so If you do not have access to the Discord, right? All right, cool, or group me or whatever. Okay, whoever has access, pay attention to these people in the chat. Send them PMs with links, please. All right, so if you don't have access to the Discord or group me or whatever it is you guys are using, please, yeah, exactly, there you go. Contact Sergio. I want everybody in on this, and I want you guys to be sharing your solutions to these problems with each other. I trust that you are adults and you will not just copy this shit down and blam it into the homework and say, fuck it, forget about it. The reason I'm encouraging this is so you can share your solutions and critique each other's solutions. What mathematicians do most of the time is we sit around at tables, we drink way too much coffee, and we argue with each other about how wrong they are with their solutions. What you guys are doing here really is writing proofs. You're writing these little mini proofs, prove that this converges, prove that this diverges. And when it comes to proof writing, you need to make sure that your logic is sound and airtight. A proof is essentially an argument with no holes, right? And you need to make sure that what you're doing amounts to that. And the only way to really do that, especially when you're first learning this stuff, is to share it with each other. So when you share something with somebody else through the GroupMe, Discord, whatever, argue with each other. Right? Look at the stuff that each other are sending critically. Don't just look at it and say, oh yeah, that's great. Look at it and try to prove that they're wrong, right? Try to argue against it. And by going through that process and trying to poke holes in each other's stuff, then and only then will you arrive at truly good arguments. So this is necessary. Again, I'm trusting you guys to be like honest and not use this to cheat. I know how online classes are, and I get that. I have a pretty good bullshit detector when it comes to exams. And if I start seeing things that look suspicious, I won't hesitate to start conduct trials and all that stuff. But use this honestly and wisely as a way to develop your logic skills. Of course, also you can share with me. Sharing with me is really good. Share with me your solutions, share with me your proofs, and especially the ones that you have concerns about. But there's nothing quite like talking to peers, right? There's nothing quite like talking to people who are at the same level you're at and are learning along with you. So text Sergio, get into that thing, and share your work with each other. All right. So I want to get a little bit more practice with the theorems from section 7.8. Let me remind you what those two theorems are. First, we have the theorem on P integrals. This is fairly straightforward. It says integrals of the form integral a to infinity 1 over x to the p dx, where a, that lower bound, is positive. These converge if p is strictly greater than 1 and diverge if p is less than or equal to 1. And we proved this last week. The other theorem that we discussed last week, called the comparison theorem, for improper integrals. This says if 0 is less than or equal to f of x is less than or equal to g of x on the interval a to infinity, and the integral from a to infinity of g of x dx converges, then the integral from a to infinity of f of x dx converges. And if the integral from a to infinity of f of x dx diverges, then the integral from a to infinity g of x dx diverges. So I'd like to get a little bit more practice with both of these things. And I want to show you a kind of picture that I think is helpful for understanding the latter theorem, the comparison theorem. When we get to talking about series, there will be a handful of theorems that are very similar to this comparison theorem for improper integrals. In fact, there's one for series which is basically identical, just applies to series instead.
How can A be greater than 0 converge if it's less than or equal to 1, it's diverge? Because if A is 1, then you would say it converges, but no, that's supposed to diverge.
No. So integrals of the form this, where A is greater than 0, converge if P is bigger than 1, and diverge if P is less than 1. In other words, these are only type 1 integrals, right? Integral 1 to infinity, integral 2 to infinity, integral 5 to infinity, but not integral 0 to infinity, not integral -1 to infinity. So requiring that the lower bound is positive just guarantees that this is a type 1 integral rather than having a mixture of type 1 and type 2. Does that make sense?
Yeah, thank you.
All right. So I want to give us a picture to think about when we're looking at the comparison theorem. For that, I'll need a little bit of color. We'll call this red function here g of x. And we'll call this light blue function here f of x. And I'll put a, I don't know, somewhere like here. So the idea is everywhere to the right of the positive number a, well, it doesn't even matter that it's positive, but everywhere to the right of a, the red function is above the blue function, which means that the blue area here is totally contained within the red area here. I'll try to adjust the contrast so you can see the colors. But the basic idea is this. Since the blue area fits inside the red area, if the red area is finite, then the blue area must also be finite. Because the blue area fits inside the red area. So if you fit in a finite sized box, you must be finite. And the converse says if the blue area is infinite, then the red area must also be infinite. So kind of the way I like to say this is if you fit in a finite box, then you must be finite in size. And if an infinite size box fits inside you, then you must be infinite in size. So it kind of goes two ways. Because the blue is contained within the red, if the red is finite, the blue has to be finite. And if the blue is infinite, then the red has to be infinite. Does this make sense? The fundamental concept here being if f is smaller than g, then the integral of f is smaller than the integral of g. If you're smaller than something finite, you have to be finite. If you're bigger than something infinite, then you have to be infinite. Any questions on the statement of either of these theorems? Okay, let's play around with one or two more examples. I know we did look at some examples last week, so I'm not going to stay here for too long. Let's play with just one or two more. Let's investigate the convergence. Which for now means tell me whether the thing converges or diverges of the integral from e to infinity of the natural log of x over x dx. We could jump in and evaluate this. This integral can be done through a u substitution. First, you would write it as the limit r to infinity, integral e to r. And then you can make a little substitution, z equals ln x. But since all I care about here is the convergence, there is a faster path. Rather than evaluating this integral, I can use my theorem. Can anybody tell me, do you think this integral converges or diverges? First, you kind of need to have a gut feeling for it, and then you try to prove that gut feeling.
Can we assume that it's a p integral since it goes from something to infinity?
No. So that's a good question. This note. This is not a p integral. It is a type 1 integral. Why is it not a p integral? We talked about this a little bit last week, recognizing whether something is or isn't a p integral. What makes a p integral a p integral? Davis is partly right there in saying that because it's a type 1 integral, right? P integrals are also type 1. Yeah, good, because the top, because ln x over x is not equal to 1 over x to the p for any value of p. Remember, if there's anything going on inside your integral besides 1 over x to some power, it's not a p integral. But it's kind of similar to the p integral 1 over x, right? If you integrate 1 over x from e to infinity, that is a p integral. So if not for the natural log, so i.e. ln x ruins the p-ness of the integral. All right, I know that's like a 5-year-old joke, but you know, it might help remember. Okay. So we've established that the thing is not a p integral, but it kind of reminds us of the p integral integral e to infinity 1 over x dx. Does the integral of 1 over x done from e to infinity converge or diverge? Yeah, this is a divergent p integral. Because p is equal to 1, which is not smaller than 1. So what we should use here is the comparison theorem. We know that for x in the interval e to infinity, that 0 is less than or equal to 1 is less than or equal to the natural log of x. All right, picture the graph of ln x. Everywhere to the right of e, it is above 1. And now if you divide through by x, you get that our function, ln x over x, is bigger than 1 over x. So this process of building an inequality is an important process to get comfortable with. This is now an inequality that looks exactly like the inequality in my comparison theorem. So I like to give it a name, call it star. We know that the integral from e to infinity of 1 over x dx diverges as a p integral so by star and the comparison theorem, the integral from e to infinity ln x over x dx must diverge also. And that's it, you're done. No calculation. Nice, right? My function, ln x over x, is bigger than 1 over x. And the integral from e to infinity of 1 over x is divergent because it's a p integral with p equal to 1, which is not bigger than 1. Therefore, the integral from e to infinity ln x over x must also diverge. That's it. If you wanted to be extra careful here, I didn't say it because we already set it up here, but here p is equal to 1, which is not bigger than 1. So if you wanted your whole solution to fit in a nice tight space from here down, right? Everything below the pen. That would be what a good solution for this problem looks like. You begin with something that we all know, that first inequality, and then you build an inequality involving my functions from that. Since the function I'm working with is bigger than 1 over x everywhere on this interval, I know that the integral of my function is bigger than the integral of 1 over x. Since the integral of 1 over x diverges, because it's a p integral, with p equal to 1, I know that my integral must also diverge because it's bigger than that divergent p integral. Any questions on the logic
Can
here?
you go to your house and break pandeones
So why
right
is,
now?
I think you might have already said it, but why is one
Oh
over
my
S
god, I'm
considered
sorry.
divergent?
I'm so sorry.
I'm sorry, Davis, could you repeat that? I lost you there.
Why is 1 over X considered diverging?
Because it's a p integral and p is equal to 1 there. So remember our theorem on p integrals? Integrals of this form, right, from some positive number up to infinity, 1 over x to the p. These converge if p is bigger than 1, and they diverge if p is less than or equal to 1. So the integral of 1 over x dx is a p integral where p is exactly equal to 1, which means he has to be divergent. You can compute this integral. It's going to be the natural log of r minus the natural log of e as r goes to infinity, and the natural log of r goes to infinity as r goes to infinity. So you can compute it directly if you want to remind yourself why he diverges. But the slicker path here is just to remember our theorem on p integrals that says integrals of that form diverge if p is less than or equal to 1.
Okay.
Is that making sense?
Yeah, I was thinking in terms of the actual equation and not the integral.
Oh, I see. Yes, definitely it's the integral here that we're talking about converging or diverging. All right. Any other questions on this fella? It's okay, Sergey. Okay. If there aren't other questions on that, then let's play a little game. And let's do one more. How's about all right. The integral A, does he converge or diverge, and why?
Converge,
He's convergent. Good. Why?
because it's a p integral with the value of p greater than 1 times a constant of 7.
Good. We want to be a little bit careful there. So if we're being super careful with our language, which is one of the things we want to train, this guy isn't actually a p integral. He's a constant multiple of a p integral. So we pop out the 7, and we see that this is a constant multiple of a p integral with p equal to 3, which is bigger than 1. Thus, he converges. All right, what about this fella, B? Careful, Alex. So the lower bound doesn't tell me whether the integral converges or diverges. right? You need to, if you want to apply the results on P integrals, you need to first check that the integral is a P integral. So P integrals have to have this positive. They're type 1 integrals. If this isn't positive, then it's not a type 1 integral. But this fellow doesn't tell you whether the integral converges or diverges. It's the power. So this fellow converges because it is a type 1 integral and the power is bigger than 1. Does that make sense? Okay, cool, cool. All right, what about B? First, is it a P integral?
I would say it is.
The integrand looks like a P integral, right? 1 over x squared, there's nothing wrong with that. But is it a P integral? What else needs to be true for something to be a P integral?
The lower bound has to be greater than 0.
Right.
There you go. Yeah.
So this is not a P integral. Because it's not type 1. There is a type 2 problem at x equals 0. Because I'm integrating from -1 to infinity, I would have to take care of the type 2 issue at 0 that comes from the infinite discontinuity here. So I'm going to put a pin in this guy. We're going to come back to him. I can split him up as the integral from -1 to 0 plus the integral from 0 to 1 plus the integral from 1 to infinity. The 1 to infinity portion, he will converge because he is a P integral, but the other two pieces will need to treat differently. What about C? First, is C a P integral?
No.
Let me quickly remind, it looks like we want a little refresher on type 1 and type 2. Remember, type 1 integrals, the region is infinitely wide. Type 2 integrals the region is infinitely tall. So B here has type 1 and type 2 shit going on. And we can only apply our result on P integrals to type 1 integrals. So the function in B, his graph looks like this. And we're integrating from -1 all the way off to infinity. So the area here, the region that we're looking at, goes up infinitely high and then also infinitely wide. So he's got type 2 stuff going on here and type 1 stuff going on here. I'm getting some feedback from somebody, so if you guys don't mind, I'm going to select the mute all, and then you can just hold spacebar to talk. So the way we would handle the integral in part B is by splitting it up as the integral from -1 to 0. That's this stuff, which is type 2, plus the integral from 0 to 1. That's this stuff, which is also type 2, plus the integral from 1 to infinity. That's this stuff. And this guy is type 1. But these two are both type 2. And our result on p integrals can have only type 1 stuff going on. That's why the lower bound needs to be positive, right? So that's why the lower bound doesn't tell me anything about convergence. The lower bound being positive is just what allows me to classify it as a p integral, because a p integral has only got type 1 stuff going on. Does that make sense? So the integral from -1 to 0, that region's infinitely tall. That's type 2. The integral from 0 to 1, that region is also infinitely tall. So that's type 2. And then the integral from 1 to infinity, that's infinitely long and not infinitely tall. So that's type 1. Can anybody, while we're here, because we've decided to take a second and talk about B, can anybody tell me whether either of these integrals, the type 2 pieces, converge? If you happen to have finished the homework, then you should be able to tell me this guy.
Is it because the bounds, or does that, or no?
Oh, well, I mean, we could just set it up. So the integral from 0 to 1 of 1 over x squared dx is the limit as r goes to 0 from the right, integral r to 1. 1 over x squared is x to the -2 dx. So when I calculate my antiderivative, I'll have lim r to 0 from the right, right? Because I'm talking about the 0 to 1 integral. X to the -2, his antiderivative, we add 1 to the power and then divide by that new power. That's -1 over x, evaluated from r to 0. So this is lim r to 0 plus, not r to 0, from r to 1. This is -1 minus -1 over r, which is lim r to 0 plus 1 over r minus 1. So what happens as r goes to 0 from the right in 1 over r minus 1? What does 1 over r do as r goes to 0 from the right?
It gets smaller and smaller, closer to 0.
R gets closer and closer to 0. 1 over r, let me show you something. Yeah, so there's a fun way to play with this. Thinking about reciprocals. As r goes to 0 from the right, well, 1 over 1, that's 1. 1 over 0.1, that's 10. 1 over 0.01, that's 100. 1 over 0.001, that's 1,000. So 1 over r, as r goes to 0 from the right, I'm thinking about r being very, very small and positive. So 1 over r is going to infinity. This is positive infinity minus 1, which is still positive infinity. So this piece diverges. So what can we say about the whole integral?
It diverges.
Right. Remember that discussion from last Friday? If any part diverges, the whole thing diverges. So since this guy diverges, I know right away that the whole integral diverges. Just for fun, does this type 1 portion converge or diverge?
Converge.
Yeah, this one is a p integral, right? The integral from 1 to infinity of 1 over x squared, that is a p integral, and here p is equal to 2. So this fellow is convergent. If you calculate the antiderivative and evaluate this whole integral, you'll find that the value of this integral is 1. It's true that 1 over x squared itself, Alex, goes to 0, but that doesn't mean that the integral has value 0. So you got to go through that whole antiderivative process, remember. So this piece is convergent. This piece we just said is divergent. What about this piece? Anyone got a feel about this? Look at the graph. Think about the symmetry of that function. 1 over x squared is an even function. So the area from 0 to 1 is the same as the area from -1 to 0. Both of these diverge. We calculated the 0 to 1 integral and found that he is divergent, and the -1 to 0 integral by symmetry is the same as the 0 to 1 integral. So here we've got infinity plus something finite. That's definitely infinity. So the integral in B is divergent. And if you wanted an explanation, you would say because this portion, the 0 to 1 portion, diverges. And you would need to show the calculation that we just did.
So we can stop showing our work after we prove that one of the segments diverge.
Yes.
Thank you.
If you have an integral that is a mixture of type 1 and type 2 or has multiple type 2 things, if you have an integral that you need to split up into multiple improper integrals in order to handle, like we were talking about last Friday, as soon as you show that one of those pieces diverges, you can stop, because automatically if one piece diverges, the whole thing diverges. Let's skip over C for a minute and look at D. Is D a P integral?
Yes.
Yes, it is. Good. What is P?
1/2.
Good. This is the integral from 1 to infinity, 1 over x raised to the 1/2 power. So this is a P integral. I know that the integrand is in the correct shape, and also it's a type 1 integral because we're going just from 1 to infinity. We're not jumping over the problem spot at 0. So this is a P integral with P equal to 1/2. So is he convergent or divergent?
Divergent.
Right. I should say thus the integral diverges because 1/2 is not bigger than 1. Right. So remember, if P is strictly bigger than 1, the integral converges. If P is not strictly bigger than 1, the integral diverges. The integral in C, is that a P integral?
Yes.
So it is a type 1 integral going just from 1 to infinity. So far that looks good. I've got just an x to the 4 downstairs. That looks like a P integral. But the inverse tangent function upstairs ruins it, right? Remember, P integrals are type 1 integrals where the thing inside is just 1 over x to the P. And what's worse, type A, in problem A here, this also wasn't a P integral, right? He was a constant multiple of a P integral because I could pop the 7 out. Can I pop the inverse tangent of x out?
No.
No, because it's not a constant, right? The inverse tangent of x, that's a non-constant function. So this is not a P integral. And there was a suggestion in chat from Alex that we should use the comparison theorem. All right, so let me see how we would do that. You notice every time I use the comparison theorem, I write the words comparison theorem at the start and I underline them to let my reader know what it is I'm doing. You should also do that. How do we get started with the comparison theorem? What's our first step? Feel free to look back in your notes. We did one of these a little bit ago. It's just a slightly different problem involving the natural log of x over x. What sort of thing am I going to be working with in my first step? Yeah, I need to pick what I'm going to compare it to. What do you think we want to compare against here? I wouldn't pick 1 over x here. So first let me ask, do you think that the integral in C converges or diverges? You want to have a guess, and then you want to try to prove your guess using the theorem.
Converges?
I think that this converges as well, because the x to the 4 downstairs gets big fast, which means 1 over x to the 4 gets small very fast. And remember, getting small very, very quickly is what's required for these type 1 integrals to converge. The inverse tangent function upstairs, what does he do? What does he look like for very, very large numbers x? If I plug like x equals 10 million into arctan x, what should I expect to be getting out?
Pi over 2.
Yeah, something very close to pi over 2, right? So I am going to want to compare against, I'd say 10 inverse x over x to the 4 is kind of similar to pi over 2 over x to the 4 for large x. But then I need to be more specific. In particular, I need to build an inequality. So I would say for x in the interval 1 to infinity, 0 is less than or equal to the inverse tangent of x is less than or equal to pi over 2. And this is coming from knowing the graph of the inverse tangent function. Hopefully I've hammered on this enough that we're all getting somewhat comfortable with that graph. Remember, its shape is kind of like the cube root. Sorry, this bump here is just coming from my papers. But yeah, should look something like this. And he has this upper bound here of pi over 2. So the arctan function, this graph, is always below pi over 2. And if we're only looking from 1 to infinity, that means I'm looking only at this part. It's true that he is both bigger than 0 and smaller than pi over 2. So that's what this inequality says, and it comes from the graph. So knowing your graph's hugely important here. Even though we're not graphing, that's not what we're doing. We're building an inequality. But the way we build the inequality is by thinking about the graph. Any questions on where this inequality came from or why I'm qualifying it in this way? Why do I say 1 to infinity here instead of 0 to infinity or 5 to infinity or something else?
Because aren't you breaking it apart?
I'm not breaking it apart, but I think you're getting at it. Where else do I have a 1 in this problem that you think this 1 is coming from?
The bound?
Yeah, this bound, right? I need to show that my function is smaller than something else from 1 to infinity. So it's important that this inequality is true over the domain of integration. I'm integrating from 1 to infinity, so I need to make sure that my inequality is true from 1 to infinity. If you look back at the statement of the comparison theorem, it says, if this inequality is true on the interval a to infinity, then you compare the integrals from a to infinity of those functions. So it's important that our inequality is true here from 1 to infinity. All right. This isn't an inequality involving my function yet. How do I make my function show up here?
Divided by x to the fourth.
Good, we divide everywhere by x to the 4, and x to the 4 is positive for any value, any x values coming from the interval 1 to infinity, so I don't have to flip over my inequalities as I would if it was negative. So I arrive at this inequality, and now I have my function is smaller than the thing I wanted to compare against, right? I said I wanted to compare against this guy, and now here he is. And I've shown that my function is smaller than him everywhere on the interval 1 to infinity. That's perfect. That's exactly what I need to use my comparison theorem. What should I say from here? So I'll label this inequality as star, just like we did in our last example with the comparison theorem, so I can refer back to it. What do I want to say from here? Remember, if the integral of the bigger function converges, then the integral of the smaller function converges as well. I'm trying to show that the integral here is convergent. So it would be sufficient to show that the integral of this guy, this integral, is convergent. And it is. Because this is equal to pi over 2 times the integral from 1 to infinity, 1 over x to the 4 dx, which is a constant multiple of a p integral, right? The integral from 1 to infinity, 1 over x to the 4 dx is a p integral with p equal to 4, which is bigger than 1. So integral 1 to infinity pi over 2 divided by x to the 4 dx converges. Hence, by the inequality star and the comparison theorem, our integral, the integral from 1 to infinity, inverse tangent of x over x to the 4 dx must also converge. So you see there's very little in the way of calculation going on here. And there's a lot of writing words. In your homework, WebAssign's just going to tell you to click converge or diverge. That fucking sucks. Please practice writing these arguments out in full sentences and share your arguments with each other through Sergio's Discord or whatever it is. Please do that. And please be critical of each other's work. If you think someone's phrasing something wrong, using the wording correctly, or if their logical flow isn't sound, if their inequality doesn't apply to that integral, whatever it is, call them out on it and make a suggestion to improve it. And on the other side of that, please be receptive to criticism from other people. Argue your point. Don't just agree with what somebody else says. Argue your point. If you think your shit is right, try to convince them. And through that argument, you will come to a sound logical process. And that's what we need. So make sure you're writing the words and make sure you're discussing it with other people so that you can double check your logic. I'm sure you guys are all aware of the political situation in the United States right now. This is what happens when nobody checks anybody else's fucking logic. So please, especially in mathematics, make sure you're checking your logic. And even though the homework doesn't explicitly require you to write out the words, write them out. Because on the test, you will need to do that, right? It's critical that you practice those skills because you will be judged according to those skills. All right. So I think this is enough on improper integrals. This together with what we did last week, you may want to go back and review last Wednesday's or Friday's videos to make sure you're comfy with all the definitions and how to do the raw calculations, because there will be plenty of moments where you need to do those as well. The remainder of the class here today is going to be about sequences. Intuitively, most of us have some notion of what a sequence is. It's an ordered list of objects. You could have a sequence of coffee cups. I tell you, this is the first coffee cup. This is the second coffee cup. This is the third coffee cup, and so on. That's a sequence of coffee cups. Most of the sequences we're going to deal with will involve numbers. So the intuitive definition of a sequence is an ordered list of numbers. Okay. You could, in theory, have sequences of things that aren't numbers. You could have ordered lists of dogs or people. But for us, sequences will be ordered lists of numbers. So like there's a first number, and then there's a second number, and then there's a third number, and so on. Right here, I've written out the first few terms of a sequence. This is the first term. This would be the second term. This would be the third term, and so on. The sequence that I started to write out here is the digits of pi, right? So you can think of those digits as being an ordered list, right? 3.1415926, blah, 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 blah. Those things have to come in that order, and they are numbers. So it is an ordered list of numbers. It is a sequence. Another way to think of these sequences and this is the more formal definition, but both are equally valid. A sequence is a function whose domain or inputs is the set of natural numbers. The natural numbers, you can use this called Blackboard bold N to represent, is the set 1, 2, 3, 4, etc., the counting numbers. Some people include 0. But basically, the important thing to remember here is that a sequence is an ordered list. There's a first term, a second term, a third term, and a fourth term, and so on. One way to think of that, if I come back to my example here, the digits of pi, I could say that this is the sequence AN having A1 equal to 3, A2 equal to 1, A3 equal to 4, A4 equal to 1, A5 equal to 5, A6 equal to 9, A7 equal to 2, A8 equal to 3, and so on. Which brings me to the notation. We said that a sequence is a function whose domain is the set of natural numbers. But instead of writing f of n, right? Usually we use the symbol f for a function, parentheses to encase the input. I wouldn't write an x here because x is usually understood to be a continuous variable, a real variable, where x can take on any real number. I use the symbol n because n is usually used to denote positive whole numbers. But instead of writing f of n, we write an a. So like the f is replaced by this a. And then instead of the parentheses, we use a subscript. To denote the output associated with the input n. And another word to say the output associated with the input n is the nth term of the sequence. This symbol here, this a with the subscript n, is pronounced like Fonzie A and then N, right? In other words, like A, N. You could say A of N, but please don't say A to the N. It's not a power, right? The N is not an exponent. So saying A to the N is quite confusing. because there will be cases where we have exponents in these things. And if you're using the to the words, it can be very, very confusing. So, you know, call it an or a of n, that's fine. A sub n, some people like because it's a subscript, but just a little bit of notation and vocabulary. Some examples. I could say find a formula for the nth term an of the sequence whose first few terms are, let's say, 1, 1/2, 1/3, 1/4, and so on. So this curly braces notation is something else that you're going to see quite a bit. If I just list the first few terms of the sequence and I expect my reader to infer from that list the pattern, then we'll put those first few terms in curly braces usually. So can somebody identify the pattern? What would be the next term of this sequence?
1/5.
Yeah, 1/5 would be the next term. And then after that?
1/6.
So what's the formula then? What is the nth term? We said A1 is 1. Let's do this. So the first term, A1 is 1. The second term, A2 is 2. The third term, A3 is 3. A4 is 4. And then as you correctly said, A5 would be 5. What is the nth term, AN?
1/n or just
Good.
n?
Yeah, 1 over n, right? Oh, sorry, I didn't, yeah, sorry. These are all reciprocals, right? Yeah. So yeah, AN here is 1 over n. If I want to refer to the sequence as a singular object, I'll put it in curly braces. If I want to refer to the nth term on its own, I won't put it in curly braces. Yeah, good question. So sometimes you choose to start your sequences at n equals 1, like we did here. Or if n started at n equals 0, then we would say AN is 1 over n plus 1, like this. And sometimes we'll like to think of our sequences starting at 0. Sometimes we'll like to think of our sequences starting at 1. Most of the time, your textbook has sequences starting at 1, and most of your homework problems will specify. It'll say, you know, find the formula for AN, assuming that the starting term is n equals 1. Sometimes I will do that. Sometimes I will start at 0 because from time to time, there are some formulas that are a lot nicer if you start at 0. Any questions on this first example here where we found a formula for AN? Okay, let's try another. So we're going to find a formula for an, assuming n starts at 1. And the first few terms of this sequence will be -1, +1, -1, +1, -1, and so on. So here, A1 is -1, A2 is +1, A3 is -1, A4 is +1, A5 is -1. Any ideas what algebraic representation I could use for this sequence?
N times a negative?
I think
Negative
getting
n
there.
to the power of, oh wait, no, it's -1 to the nth power.
Good, right? -1, that's -1 to the 1. +1, that's -1 to the 2.
I see.
This guy can be thought of as -1 to the 3. This guy can be thought of as -1 to the 4. This guy can be thought of as -1 to the 5. So one way of writing an is as -1 to the n. Can anybody think of another way to do this? Maybe involving some trig functions? What is the cosine of pi? Cosine of pi is -1. But the cosine of 2 pi, that's +1. Yeah, that's okay. The cosine of 3 pi is -1 again. The cosine of 4 pi is +1 again. If you think about it, at integer multiples of pi, you're jumping back and forth between this guy on your unit circle and this guy on your unit circle. So another way of writing this would be an equals cosine of n pi. And if there's a way to do it with cosine, there's a way to do it with sine also. The sine value up here is +1, and the sine value down here is -1. These guys come from angles that are integer multiples of pi. These guys come from angles that are integer multiples of pi over 2, or actually odd integer multiples of pi over 2. So not quite sine of n pi over 2, because then if I plugged in n equals 2, I would land here. And if I plugged in n equals 3, I would land here. That's good, but then n equals 4 would land me here. So another way to do this would be to look at the sine of pi over 2, the sine of 3 pi over 2, the sine of 5 pi over 2, the sine of 7 pi over 2. This would be the sine of 2n minus 1 times pi over 2. Or let me think, 2n, if I'm starting at n equals 1, it'd have to be 2n plus 1 times pi over 2. Odd multiples of pi over 2. Like 3 pi over 2, 5 pi over 2, 7 pi over 2, the sign of those jump back and forth between plus and minus 1. You don't see this third one that often, but you do bump into this guy from time to time. So I wanted to show you that cosine of n pi does the same thing as -1 to the n for positive integers n. Cool stuff, right? Maybe, yeah, I mean, certainly there's a way to do it with tangent. You would have to figure out how you land here, and then here, and then here, and then here. So if you look at the multiples of pi over 4, as long as they don't land you here and here, that would work with the tangent function. But there's no nice way to write numbers that are not congruent to 2 or 4 mod 4. So yes, you could do it with tangent, but there's not an easy way to write the algebra formula for it. It'd be easier with secant and cosecant, honestly. But tangent and cotangent would be a little bit tricky. But let's not dwell there too much because that's not super important. I just wanted to show you this and relate it to this. Same game. And again, we'll assume n starts at 1 for this guy. And again, let's assume that n begins at 1. First, you need to detect the pattern. What do we think the next term in this sequence would be?
1/9.
Good. And then?
1/11.
Good, good. Okay, so what's the pattern overall?
It adds 2 to the bottom.
It's true that, yep, we're always adding 2 to the bottom. So I can think of this as 1/1, A1. A2 is 1/3, which is 1/1 plus 2. A3 is 1/5, which is 1/1 plus 4. A4 is 1/7, which is 1/1 plus 6. So in general, what's going on here? AN is 1/1 plus what? Yeah, 2n, right? Except what's wrong with this? This is fine if n started at 0. But I want to figure this out where n is starting at 1.
It would be 1 plus 2 times n minus 1.
That works. Yep. Like this. This works great. Another way to write that is like this. right? Distribute the two, collect like terms. Okay, so how are we doing? Yeah, this is where I'll leave it for here today. We're a little bit over time. I appreciate you guys hanging around these last 5 minutes. Next time, we're going to start talking about convergence of sequences. So there's a whole new concept of convergence that we apply to sequences, totally different than for series. And that's what we'll begin on next time. And that's what the majority of your homework this week is going to focus on. I want to do one more thing before I let you go. Please read section 11.1. Please read it in the textbook. I know we're not used to having to read books in math classes. Take the time to read section 11.1. It's a long section, and 11.1 and 11.2 are foundational for the hardest part of this class, which is series. Okay, so read section 11.1, and then next week we'll talk about 11.2. You can read that as well if you want, but make sure you read 11.1. It'll make this week's homework much easier. And next time when we're talking about the theorems from 11.1, it will be very helpful to have read them before class. So please read 11.1. All right, work on finishing up the homework from last week. It's not due till Wednesday, so if it's not done, don't panic. You don't need to submit any extension requests, just work on it. Get that done by Wednesday. Make sure it's completely done by Wednesday. And then if you want to, go ahead and get started on homework 6, which I'll be opening up a little later today. All right, if you want to talk problems, I'll have an office hour this afternoon, 3:30 to 4:30. Exam 1 scores should be up by tonight if I'm able to get them done by like 9 or 10. Otherwise, I'll get them up tomorrow, I promise. Have a good afternoon, guys, and I will see you next time.
Have a good day.